All right, we're going to continue our review for the next 2 days of final examination from last semester. And today I'm going to cover 4 more problems. I covered 4 problems on Monday, and so we'll go move 4 more problems forward today, and then we'll do the remaining 4 on Friday. So this particular problem looks at the concept of error. Error is one of the performance criteria for control system. And so what that means is we're interested in studying the behavior of this particular signal here, which is the output of the summing point. Okay, and so again, what I'm going to do today, as I did on Monday, is cover the general concepts or the underlying principles that I'm looking for in these different problems. So there's several different ideas here that can be used. First of all, the issue of steady-state error only makes sense if the system is stable. So the control system must first of all be stable. Okay, so a lot of the equations or techniques that we'll cover in a few minutes here only apply if the signals that we're looking at are bounded, and so we do have to ultimately check for stability of the system. So bear that in mind. The second idea is the idea of the transfer function between the reference input to the error signal. Okay. And then we have to also know what are the models of the input. We have to understand what to do with that piece of information. And so, for example, in this problem, part A, it says find the error for a unit ramp reference, and I give the ramp reference model, and so that's what this point is here. One of the techniques that can be used is to appeal to the final value theorem in Laplace transforms, and so there's the Laplace transform principle. There's a principle here called the final value theorem. It tells us what is the final value of a signal in time, given that we are working with models in the S domain. And so, as is common in this course, we will use the S domain expressions, but we're really interested in knowing what is the steady state. Steady state. This is a time steady state in time question, and so the final value theorem tells us what is the value of that signal in time, given that we're playing with all these equations in S, which is a different domain. And then finally, if we do this regularly enough, we start developing patterns. And one of the things that we can do is we can take a look at what is known as the system type. And the type can tell us a lot about the steady state error for some of the common reference inputs. And so let's go ahead and step through these 2 problems that are on this page and try to review some of these principles. The first problem looks at the steady state error for a unit ramp reference, and what is given here is the model of just this block alone. But we're looking at the behavior of a control system given that we know this model. The second problem is similar, but we want to look at the case where the input is a unit step, and so with the unit step, the signal R of S is going to be 1 over S. Okay, and the model is changed, and what's different here is that we have a variable k which can be designed, and we want to find out what is the upper limit of that value of k. We want to see if we can meet a particular error specification 0.01. So let's first take a look at the first problem, and we will take a look at this system and find the closed loop model. This is the transfer function from E to R. E of s over R of s. Again, appealing to what we saw in earlier problems, we would use the forward gain from R to E. That's going to be equal to 1 divided by 1 minus the loop gain. The loop gain here is going to be G with a minus sign, so the minus sign cancels that, turns into a plus, and so we have 1 over 1 plus G of s. Now we substitute this model here, and so what we have is 1 over 1 plus 10 over s plus 1. Okay, my pen kind of slipped here a little bit. There's a plus sign there. We can clean that up a little bit, and what we get is the relationship s plus 1 over s squared plus s plus 10. Okay. Now the first thing we should check is whether or not this is a stable system. And so we should check stability, and so we need to examine the roots of s squared plus s plus 10 equal to 0. In other words, we want to find the poles. And we can stick that into our calculator and check it out, and we discover that everything is good. So from here on out, any additional equations that I apply, for example, the final value theorem, is going to be a valid approach. If I apply the final value theorem and do not check stability, then I'm not sure that the final value theorem outcomes are valid. Okay, so we'll now look for E of s. So E of s now is going to be this expression that we calculated, s times s plus 1 over s squared plus s plus 10, and then we multiply both sides by R of s, and that cancels our R of s over here, and then we need to put R of s on this side, and so we have R of s is 1 over s squared. So this is the expression for E in the Laplace domain. But our question is, what is the value of this error in the time domain, steady state? So now we go down to the next principle, and that is to take a look at the Laplace transform final value theorem. We know we can apply it here because we've checked stability, and so we can go forward, and now we say that E steady state, that's the same thing as E as time goes to infinity, is equal to the limit as s goes to 0 of s times E of s. Okay. So this expression now is a valid expression. This is the Laplace transform final value theorem. It's a valid expression because we check stability to ensure that the signals in the system are bounded. So let's go ahead and apply that principle here. We need to take this expression, we multiply by s, and there's some things that cancel out, so we have s here and an s here. That's s squared. That cancels out the s squared here. So there's some things that cancel out. This cancels with this. Now we let s go to 0, and what we are left with in the end is the answer is 1 over 10, if I've done my math right. Okay. And this is a valid number. It's a number that can be trusted because we've checked that the system is stable, first and foremost, and then we apply the final value theorem. So it's a straightforward application of some basic linear system concepts. Now we can do the same thing, again, same approach for this problem. It's a slight wrinkle here. What we have now is we have a variable here that can be adjusted, and we're trying to see if we can get a gain, an error less than 0.1. The plant model has changed a little bit. But applying the same idea here, what we're going to find here is E of s over R of s. If we find the closed loop transfer function model, we're going to get on the top, we're going to get s plus 1 cubed. On the bottom, we're going to get s cubed plus 3s squared plus 3s plus 1 plus k. Okay, this is just cleaned up. I've expanded s plus 1 cubed, and after all the algebra is done, we get this expression. Okay, and so now what we have to do is we have to check stability. We have to check stability, and by examining the roots of s cubed plus 3s squared plus 3s plus, and the constant term is 1 plus k equal to 0. Now, in this particular case, k now is a variable. And because k is a variable, the roots are going to change. And so we need to find the range of k for which we have no poles in the right half plane. And so a tool that we have exercised already in a previous problem is the Routh-Hurwitz. And so Routh-Hurwitz can be applied here. Or alternative, you could pull out a calculator and do a quick check of some variables, some numbers here. And just by doing a search, you can quickly narrow your range of k down. But we'll go ahead and perform Routh-Hurwitz here and see what we get. We get s cubed, s squared, s to the 1, s0 to set up the Routh table. And then we start off by populating the first two rows with the coefficients of this polynomial. So we should have a 1 from the s cubed, a 3 from the s squared, a 3 from the s term, and then a 1 plus k is the constant term. Okay? And then if we apply the Routh-Hurwitz table formula to find these coefficients, one formula we have to find here is B0, and then this last coefficient here we'll call C0. Okay? And it turns out that B0 is going to be, in this case, it's going to be negative the determinant of 1, 3, 3, and 1 plus k, and then we have to divide by 3, this number right here. So you'll want to review the Routh-Hurwitz process. And so basically, this ends up giving us, if I do my math correctly, I think this is 9 minus 1 plus k over 3. C0, it turns out, if we go through the same process, if we do everything correctly, it will end up being 1 plus k. One of the sanity checks you may recall is that when you look at the last elements of the even-powered rows of s, they should be the same. So here's an even-powered row of s, it's s squared. The last coefficient is 1 plus k. Here's another even-powered row of s, and it should also have its last element, 1 plus k, if you've done your math correctly. Of course, what I typically do is just simply, because I've done this often enough, I just simply put 1 plus k right here. So basically, from these two conditions, we get two conditions here for stability. We get that 8 minus k has to be greater than 0, and 1 plus k has to be greater than 0. And so our conclusion is that k has to fall in the range between 1 and 8. Okay? So as long as k is in the range between 1 and 8, we are okay, if I've done my math correctly. But now we can go and do our error analysis. Our error analysis says that we want all this to be less than 0.1. So we'll go through the process, and we can see if what k needs to be. See, k is a variable here, and we just basically want the final value theorem equation. We set that up. We take the limit as s goes to 0 of s times e of s, and we want that to be less than 0.1. Okay? But here, k is going to be a variable inside this expression, and so we can solve for k and see if it falls inside this range. Okay? Now, I said another way that we could approach this problem is to also appeal to the idea of system type. System type. And so system type says we take a look at a system, we take a look at a control system, and we take a look at the loop function. The loop function in this case is just g. And so in this case here, what we can do is we can take an alternative approach. It's all based on the same equations, but it's just take a look at this. We can take a look at and say that the system type is equal to the number of poles at s equal to 0 in the loop function. Okay. Now, the loop function in this particular case is g of s. So we look at k over s plus 1 cubed, and we would conclude that the type is equal to 0. It's a type 0 system. So a type 0 system, we'll recall, has finite steady state error. And so there's a formula for the error for a unit step. If it's a unit step, we put a 1 here. If it's not a 1, we put the amplitude here. And then we divide by 1 over the position error coefficient, 1 plus the position error coefficient. And here, the position error coefficient is found by just taking the limit as s goes to 0 of the loop gain. And the loop gain in this case is just g of s. So, which is this function. So if we let s go to 0, then we get, in this case, it's just equal to k. And so we see that the steady state error is equal to 1 over 1 plus k. And we want that to be less than 0.1. And so basically we say that k here needs to be greater than or equal to 9. But we see that that conflicts with this result. And so our conclusion is that it is impossible for us to increase the gain to a point where the steady state error is going to be less than 0.1. And so in this case, the solution is impossible. And so the explanation of the reasoning is that the stability falls apart. Okay? So let me kind of zoom out a little bit so you can take a look at both of those problems. It's a little bit difficult on a wide screen to look at things that are tall, but that's kind of the general idea there. Okay, so the basic principles are, first of all, check stability of the system, understand how to derive the correct transfer function. Okay, sometimes students will look at this output. They'll look at y and try to derive the transfer function from here to here, but that would not be the correct approach. Understand how to apply the model of the reference input, this signal here. Know when it is valid to apply the final value theorem. It comes back to this question of stability. And alternatively, you can apply the system type equation. Again, the system type equation and the final value theorem, they come from the same root principle of system analysis, and they only are valid if the system is stable. So those are the chief concerns that we have there. Okay, let me pause and see if there's any questions. Yes?
Can you post these, please?
The question is, can I post these? I can post today's. I'll have to see if I have Mondays. Okay, I may have thrown Mondays, but if I have them, I'll post them. There's no problem. Okay, next question, sensitivity. Okay, so the question is, what is the effect of sensitivity on control systems? This was a topic that was covered in a previous semester. We didn't cover it this semester. Okay, sensitivity was left out this semester, but I'll just give it as a tidbit if you're interested in it. If you have a model, let's call it the model T of S, T for transfer function, then sensitivity to a parameter, say the model has a parameter, let's call it alpha. Inside this model there's a parameter alpha. Then sensitivity is this function. It's called S. It's the sensitivity of the model T with respect to the model alpha. And since our models are with respect to S, it turns out the sensitivity function will also be a function of S. But it's the definition is simply to take the derivative of T with respect to alpha and then multiply alpha and then divide by T. Okay, so this is just an application of an equation. Okay, so in our particular case here, we take that same idea and we're looking at this model here. And the model is the model of an undamped natural frequency, 1 over the square root of LC. And somebody says, what is the sensitivity of the undamped natural frequency with respect to C? And so what we would have to do here is we're calculating the derivative of this function, 1 over square root LC, with respect to C. Take the partial derivative, then multiply by C, and then divide by the original model. And so this is just a set of calculus operations for us to do, a little bit of algebra, and then you end up with a number or an expression. Do the same thing again down here. So what we would do is we would calculate the derivative of 1 over square root LC, but we do it with respect to the variable L. And then we multiply by L, and then we divide by the original model. So there's just a bunch of algebra here to do, and just a little bit of calculus. This is the sensitivity of the undamped natural frequency with respect to L. Okay, so we didn't cover this topic this semester, so you won't see this problem this term. Okay? The frequency response, these are Bode diagrams, and so we are drawing here straight line approximations for both the magnitude and the phase diagrams. And so we're given a model here. The model has both first order factors. Let me see if I can get this into focus here. It has a first order factor in the numerator, a zero, a real zero. So it has a 0 at omega equal to 400. It has a pair of poles at omega equal to 20, 2 poles, and it has 1 pole at the origin, pole at omega to 0. And so one of the key things is being able to identify all the corner frequencies and knowing which corner frequencies will appear on the graph and which one will not. It's understanding what is this funny looking graph with the oddly spaced lines, understanding that this is a logarithmic scale. So in doing the frequency response, one has to understand that this axis here is going to be frequency. And the default while we're in school is that the units are radians per second because we're looking at the frequency omega. On a machine, on a piece of hardware, it's typically in hertz, cycles per second. But in academic work, where the variable is s, this is frequency. And so one of the graphs should be labeled magnitude or gain. You can call it gain. And we have to work in decibels, dB, and we have to understand what is the concept of a dB. And dB in this case is 20 times the log base 10 of whatever number we're working with. This is different than electromagnetics where the multiplying factor here is a 10. So we had to understand what this is to draw our figures. The second figure in the Bode diagram should have, as again, this axis labeled as frequency. And the default should be radians per second, radians per unit of time. Except this axis here will be labeled phase, and the default is usually units of degrees. Okay. All right, so that's kind of the big picture right there. It's two plots, magnitude versus frequency, magnitude versus frequency, and phase versus frequency, and that's how we set things up. And then what we need to do is recognize that not all of the corner frequencies, not all these numbers can appear on a logarithmic scale. In particular, the frequency omega equal to 0 will not appear on this axis, but it does affect the shape of the response. And so we need to set up the frequency axis. We need to know how to use these oddly spaced lines. And so we zoom in a little bit here. And looking at the numbers that we have to put in place here, we might call this unit here, let's call this one 1, and we'll call this one 10, and call this one 100. We'll call this point right here 0.1, and this one right here 1,000. So we label the major axes appropriately. So we need to be able to identify what are the major grid lines. Okay, these are the major grid lines that I'm going to kind of highlight right here. And then the minor grid lines are the particular frequency axis. So we need to understand how to properly read the frequency axis on a logarithmic scale. We see that we have several corners that we have to deal with. We have corners at 20. 20 is right here. We have 2 corners right there. And then we have another corner at 400. So this is 100, 200, 300, 400 is right here. And so we have another corner here. And then we need to understand how to, that the straight line approximation is basically just a series of line segments. And we need to know what their slopes are and how they change basically as we sketch this figure. And so taking into account the fact that there is a pole at omega equal to 0, it says that the initial slope should be negative 20 dB per decade. So this is a decade. And so there's the concept of a decade right here. A decade is a multiple of 10. So from 1 to 10 is a decade. From 2 to 20 is a decade. From 20 to 200 is a decade. We'll label our vertical axis here appropriately. Maybe we'll call this one 0, 20, 40, minus 20, minus 40. Okay? So the initial slope for this system, to account for the fact that there is a pole at omega equal to 0, should be negative 20 dB per decade. And the way we would set that up is we would find omega equal to 1 and 0 dB, and we would find this point right here, and we would sketch in that initial slope. This is the initial slope. It's going to be negative 20 dB per decade. And this is due to the fact that we have a pole at omega equal to 0. Now, one thing that needs to be done is we need to decide whether the slope is in the correct place. I said we start off by finding this point, omega equal to 1, 0 dB, this pair right here. And we draw the line through there. But depending on the gain of the system, the Bode gain of the system, we need to shift this line. And so there's the concept of the Bode gain. The Bode gain is very similar to the DC gain in the sense that we let s go to 0 everywhere. But if we take a look at this function and we let s go to 0 everywhere, well, at the top we'll get 400, and the bottom we'll get 20 times 20, which is 400, so that cancels. Here we'll get 100, but when we get 0 right here, we're going to end up with a divide by 0, which is infinity. And so infinite gain cannot be plotted on this axis. And so what we do is we realize that the line here is going to be shifted, however, by what is known as the Bode gain. And so the Bode gain is, again, letting s go to 0 everywhere, except we ignore this factor right here. We ignore this pole at omega equal to 0. And so then what we find here is that the Bode gain is 100, which translates to 40 dB. Okay, 100 translates to 40 dB. So there's the concept of the Bode gain that we have to be familiar with. And so that means this line that we sketched in earlier has to be shifted up by 40 dB. So we need to shift it up by the Bode gain. And we need to draw the line then, like so. Okay? And so we would draw this line like so, and we basically extend the line until we hit a corner. And so the corner that we hit here is 20. And at 20, we say what is happening, and we say that we have 2 poles. Now, each pole will change the slope by a factor of 20 dB per decade. And so this particular problem, we have 2 poles, and so the change in slope should be 40 dB per decade. So we should draw something, a new picture, which is looking like it's falling down at about 60 dB per decade. Now I'm going to try to sketch that. It's going to look something like this. Okay. And so at this corner right here, we know that there is a change of minus 40 dB per decade. Okay. And so I'm looking for some sort of annotation that says I recognize what the proper change is because there's 2 corners. Or you can annotate it here and say this is minus 60 dB per decade. Okay. And then we'll continue that line to the next corner, and that next corner is right down here at 400. And at 400, we'll take a look and see what happens is we have a single 0. And so the change is going to be a positive 20 dB per decade. And so the overall slope then is going to be, negative 40 dB per decade. the change here is plus 20 dB per decade. So that's how we quickly sketch the magnitude characteristic for the Bode diagram. We need to do something similar for the phase diagram. So we'll come down here to the phase diagram. We're going to put in all the corners. I'm going to change my frequency axis a little bit here because the corners are going to be different. And so I'm going to put 1 down here and put 10 here, 100 here, 1,000 here, and 10 to the 4th right here. Because the system now have corners in different places. The magnitude plot had corners at 20, so the phase plot is going to have corners a decade below, which is 2. So there's going to be 2 corners at 2, and there are going to be 2 corners at a decade above, which is 200. 200 is right here, so there'll be 2 corners right here at 200. All right. Now there's another corner at 400 in the magnitude plot, which means that in the phase plot there should be 2 corners. There should be 1 corner a decade below at 40, 20, 30, 40 right here, and another corner at 4,000 right here, 4,000. Okay. And so we just have twice as many corners as to deal with as we have with the magnitude plot, just more corners. And so with phase corners, the idea is a decade above and a decade below the magnitude corners. Okay, that's one basic concept. Now, obviously, there's one corner for which this doesn't apply. That's omega equal to 0. A decade below 0 is still 0, and a decade above 0 is still 0. And so what that does is it doesn't change anything here. What it does is it affects where this figure is going to start. And so we might label this, for example, we might label this as 0. Maybe call this 90 degrees, 180 degrees, minus 90 degrees, minus 180 degrees, and so forth. Now, starting again at the lowest frequency, we see that we have a corner at a pole at omega equal to 0. And since there's a pole at omega to 0, it means that the phase should initially start off right here at minus 90 degrees. Okay? And then we come in and we start adjusting the slopes every time we reach a corner. And so the adjustments are just a little bit different here. First order corners, they are going to be adjusted either plus or minus 45 degrees per decade. Second order terms, second order corners should be adjusted plus or minus 90 degrees per decade. And that's the basic idea. If it's a 0 involved, the change is plus. If the change involved is a pole, then the sign will be negative. Okay. Again, these ideas only apply for the case where all of our coefficients here are equal to are all positive numbers. You see all the coefficients here are positive numbers in this case. We saw in one of our lectures that if you have a minus sign here, anywhere, somewhere in here, all these ideas here, plus or minus 45 per decade, plus or minus 90 per decade, go out the window. One has to be very careful if you're going to do things manually. Everything that I've written down here just applies for the case where the coefficients are positive. But basically, we're going to go through, and every time we encounter a corner, we're going to adjust the slope in the same way that we handled it in the magnitude plot. Now, as a sanity check, we should ask ourselves what should be the phase out here at high frequency. And one thing that we should remember is this concept of the relative degree. The relative degree is the number of poles minus the number of zeros. And in this particular model, we have a total of 3 poles, and 1 0. And so in this case here, the relative degree is 3 minus 1, it's equal to 2. And for a model where all the coefficients are positive numbers, it means that at high frequency, the phase should be negative 90 degrees times this number. And so we should end up down here at minus 180 degrees because the relative degree is 2. So after we do all of our changes up and down, all that sort of stuff, we better end up out here at minus 180 degrees. So we're going to start it here in this problem at minus 90, and we're going to end up out here at minus 180 degrees, and there's going to be some motions here in the middle with different slope changes. Similar type of concept as you would demonstrate up here, but just twice as many corners and making sure that things start and end in the correct location. As I said in class, sketching a Bode diagram is really not a useful engineering skill anymore in practice because we typically will do things on the computer, but it's useful to know what to be looking for, what types of characteristics to be looking for, the general shape of things, so that when we do our computer work, what we see on the computer screen should jive with what we have in our minds. If not, we've either entered in something incorrectly on the computer, or we have some understanding of our model that maybe needs to be examined in greater detail. So that's the primary usefulness of being able to sketch the Bode diagram. The last problem here that we'll cover today is the concept of stability margins. And stability margins are to basically take a look at how stability of a feedback system, stability of a control system, using just the open loop models. And so stability margins, again, we use the open loop model. We use the open loop model to predict feedback system behavior. And we can do this both on Bode diagrams as well as the Nyquist diagram. The Nyquist diagram is another frequency response plot, but it's done basically, you can think of it in polar coordinates in one interpretation. And so there's 4 things that we have to understand when we look at stability margins. We have to understand what is known as the gain crossover, the phase crossover, the gain margin, and the phase margin. And so the gain crossover is basically looking at where the gain crosses over the number 0 dB. And so we take a look at this right here. And we see that this is the gain crossover right here. We'll label it as GC. And we characterize it by finding out what this frequency is here. So this is 1, this is 10. And so this looks like it's probably, this is what, 2, 3. This is probably on the order of maybe 2.4-ish. Okay, that's the gain crossover. We continue extending that line down until we hit the phase. And then what we do is we take a look at the actual phase and see how far it is away from the line 180 degrees. And that's what this dashed line is. And so this is the phase margin. The phase margin is always measured with respect to 180 degrees. So always start from 180 degrees and draw a line toward the phase curve. And so this is in the upward direction, so this is the positive phase margin. And so this is a positive phase margin. And looking at this one, I would say that's probably on the order of maybe 60 degrees. Okay, maybe 60 degrees. It's a positive 60 degrees. Okay. The other, so we've taken care of the gain crossover. The phase margin is measured at the gain crossover. The other idea is the gain margin. The gain margin is measured at the phase crossover. So we have to see where the phase crosses 180. And so that's this point, and we'll call this the phase crossover. And so this frequency, this is the phase crossover frequency, looks like it's on the order of about, let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, probably between 5 and 6, and so it's probably on the order of approximately 5.5. But we extend that line up, and now we go to the gain curve. Now the gain curve, the gain margin is measured differently. We'll measure from the gain curve to 0 dB, and so we measure this way. So it's done a little bit differently than the phase margin. Phase margin, you start off at the reference line, 180, and you draw to the phase. Gain margin, you always start at the gain curve and draw to the reference line, which is 0 dB. And so this then is our gain margin, which looks, to me, if I eyeball that, looks like probably on the order of about a positive 12 dB. Okay, so that demonstrates how to do this on the Bode diagram. Then we look at the a Nyquist plot, and we take a look at we want to apply this Nyquist stability criterion. We can also look at the margins here. Let's first take a look at the Nyquist stability criterion. And we're told that the plant is known to be stable. The plant is known to be stable. This is a partial diagram. In other words, it's a frequency response of our function of some model that's been given to us. And this is given for positive frequencies, omega greater than 0. And what we want to do is we want to say, we want to complete the diagram. And one of the things that we should know is that to complete the diagram, we would sketch the negative frequencies, and the negative frequencies will be symmetrical. So you can put in a dashed line, maybe that looks a little bit like this. Try to draw your best mirror image of the solid line, and so draw it something like so. And so this will be the frequencies less than 0, okay? And understand how the arrows should orient themselves. Okay, and then understand that to study stability of the feedback system, there's a formula that says Z is equal to N clockwise plus P. P is the number of open loop poles. In the right half plane. And we're told that the plant is stable, so the open loop is going to be 0 in this particular case. And then in this particular case here, now we have to take a look and see how many times this plot circles around the point -1, and the point -1 is right here. And so we see all these loops, and we see how many times is this thing going around -1. And so what I do is I draw a line here and see how many times this crosses in the clockwise fashion. So here's one clockwise encirclement, and here looks like a second clockwise encirclement. So here in this particular case, N is equal to 2. So I add the two together, and Z is equal to 2. Z here is the number of control system poles. In the right half plane. And so since the answer is 2, our conclusion is this is an unstable system. Okay? So the concept here is understanding what is this formula, Z equals N plus P. What are Z, what is N, what is P, what is their relationship to this picture here. We could have also asked about stability margins on Nyquist plot. We've exercised that, so let me spend a little bit of time doing that one. Maybe what I'll do is let me just redraw this picture right here. It looks something like this, okay? And here's -1. And so what we do is to find the gain crossover, we have to see where this plot crosses over a gain of 0 dB. 0 dB is a gain of 1, and so we can get an idea of what that is by looking at the unit circle. The unit circle has been kind of sketched and right here with a dashed line. And so here's a unit circle. And so this unit circle is equivalent to 0 dB up in the Bode diagram. The Bode diagram, 0 dB is a gain of 1. Gain of 1 on the Nyquist plot is this curve right here. And so the gain crossover is going to be this point right here. This is the gain crossover. So at the gain crossover, we can take a look at the phase margin. And so what we do is we draw a line to the origin, and then we measure, again, from 180 to the curve. So we go from 180 to this curve. Okay, this is the actual phase. And now we're measuring this. This is the phase margin. Okay, this is the phase margin. Now, on the Nyquist plot, we have to understand what is positive phase and what is negative phase. And the way I've drawn this arrow, this is a negative phase margin. This is a negative phase margin. So we'd have to eyeball that, and we could probably say this is probably on the order of -45 degrees. negative 45 degrees at this gain crossover. We recognize also that on the Nyquist plot, there are no frequency scales, so we cannot tell what is the frequency. We cannot say, oh, the frequency is at a particular number, because there are no numbers for frequency on the Nyquist plot. We just have to say, here's the gain crossover, okay, if we're doing it by hand. Now, the computer can tell us what it is when it draws this diagram. For gain margin, we have to find the phase crossover. And so the phase crossover is where the curve crosses over 180 degrees. So 180 degrees is out here on this axis. And so this particular curve has two gain crossovers. It has this one and this one. So these 2 points are the gain crossovers. Okay, there's multiple gain crossovers. And so the margins in this case is going to be 1 over the number. So let's take this number as an example on this scale. Here was 1, here's 1.5, so this is 1.25. And so if I take a look at the phase crossover, the first phase crossover is at negative 1.25. And so the gain margin, I would write, is 1 over 1.25, 1 over the magnitude. There's another phase crossover right here. The phase crossover for the second case, it looks like it's on the order of about 1/2. And so the gain margin is 1 over 1/2, which is equal to 2. Yes, if I've done my math. Okay, so we would have to, we would get two correct answers for gain margin. This is not in dB, though. If you express it in dB, this is 6 dB. And this one, I don't know what it is. You have to pull out a calculator. Okay, so that's problems 5 through 8 from the spring. Again, the sensitivity problem won't be on your exam. So I'll go and try to dig out these things and post them on Canvas. So we'll cover the rest of the problems on Friday.